Okay, hi everyone. Welcome to Wednesday's lecture, the last lecture of the week and almost the last lecture of the semester. We have one lecture to go on Monday, and if you bear with me, I'm going to try to get through all of the material in today's lecture, and then that allows us to spend 2 hours on Monday doing exam review. So I think hopefully it's agreeable to the students that we kind of rush a little bit today to reserve all of the 2 hours on Monday for exam review. Before we jump into it, a few things. So in the 10 minutes before class started, there were two songs, I guess, from YouTube that I showed you. The first one was Final Countdown from a band called Europe. I think they're mostly a one-hit wonder, but it's a fantastic song. And the second one was Ozzy Osbourne, Crazy Train. And if you don't know who Ozzy Osbourne is, he's a really interesting person. He had a really quite a life actually back in the 80s, and him and his wife Sharon are quite a power couple. Anyway, both very interesting people. But the image you saw there of Ozzy, as you know, on the album cover there, he was around 32, so he's around my age. And I'm just thinking to myself, man, that guy was way more successful at 32 than most of us. But you get to a point where you kind of realize, you hit 32. What have I done? I mean, I think Einstein published his theory of relativity and the photoelectric effect before the age of 25. Or something in and around that age, and here I am over 25, thinking, well, I don't have a Nobel Prize for anything noteworthy. I'm over 25, and Ozzy was in, I think, 32 when he released Crazy Train, which pretty much made him famous. So anyway, those two songs are relevant in today's lecture, so you don't need to have listened to them in advance to appreciate the lecture, but if you were one of the people who were kind of in the Zoom meeting in the 10 minutes prior to class starting, you'll have a little bit of an Easter egg when the class, somewhere in the lecture today. Before we jump into things, I just want to remind students that we have a midterm on Saturday, and we're using a new platform, Crowdmark. We've recently obtained a license for Crowdmark, so we were not able to use it for term test 1. It's not that I was just neglecting it, we weren't allowed for term test 1. So it is a new system. So please, I will remind students that I have the Crowdmark sample assessment posted. As of right now, you can see, I'm sharing my screen, you can see that only 31 people, 28 for the other question, but only 31 people out of 150 almost have bothered to even practice submitting. And how many people are in the lecture right now? There's 38 people in the lecture right now. So by the pigeonhole principle, there are some people in the lecture, at least 7, who have not tried to upload, probably more than 7, I don't know. So please, I do not want any technical problems on Saturday for the test. In fact, I will come right out now and say they will not be valid. I've posted the sample assessment last Friday. You can see here it was posted on June 5th at 6 p.m. So students will have had more than a week to practice with it. And only 31 of you guys have taken advantage of that, which is your prerogative. If you don't want to spend time ahead of time making sure your test is going to go smoothly, I don't know why you would do that, but if you choose to not do that, then that's on you guys. But then come Saturday, if you have any technical difficulties, do not come crying to me, because I've given you ample opportunity to practice this in advance. Okay, I'm just reminding that for everyone to listen to. That way it's on the recording, and if anyone complains later, I can point back to Wednesday's recording and say, look, I've given you guys a week. Okay, anyway, without further ado, I think we can jump right to, let's see here, right to the lecture. And of course, there we go. OneNote is being a little bit not fun. Okay, my keyboard off. Okay, so we left off yesterday talking about oscillations and waves. We spent a lot of time introducing the idea that there's a new type of motion. We've studied linear motion, we studied rotational motion, and we had some options, I suppose, to finish this class off with, and we chose oscillatory motion. So it's just a new type of motion, and we studied simple harmonic motion with a mass on a spring, where we learned that the motion is caused by Hooke's law. It's caused by the restoring force of Kx. And we also looked at a swinging pendulum. And assuming the small angle approximation, a pendulum is also simple harmonic motion, where the restoring force is proportional to the displacement. And we developed some equations based off that. We figured out that simple harmonic motion can be modeled by a sine curve or a cosine curve. And we learned some properties of simple harmonic motion, where we learned the accelerations are maximum at the endpoints, and the zero minimum at the center, and the velocity is the opposite. The velocity is zero at the endpoints and a maximum at the center. And you can use conservation of energy to sort of figure out the balance between the potential energy and the kinetic energy. So there's not a whole lot of depth in terms of rigorous physics theory. The concepts are pretty straightforward. It's just a matter of getting your hands dirty and your feet wet with some practice problems. So today's lecture, we're going to move forward with sound. Spoiler, sound is also a wave. So there's some oscillatory motion in sound, but sound is something audible. You can hear sound and experience sound. So there are other interesting properties of the wave that relate to what we can hear. So that's what we're going to explore in today's lecture. Okay, so first we're going to start off with talking about characteristics of sound in the same way that we kind of started off with talking about the characteristics of simple harmonic motion. And then we're going to talk about how those characteristics impact what we actually hear on our end with the ear. And hopefully we have enough time. Then we're going to proceed to talk about a phenomenon called beats and the Doppler effect. And it's a really cool phenomenon. So I'm hoping we have time to get to that today. Okay, so here's a recap that I pretty much sort of verbally said. Sound is a wave. Spoiler alert. Waves can propagate. So we've talked about previous waves. We've talked about oscillatory motion with mass on a spring. The source of that oscillation. So the oscillation here would be something like the mass oscillates back and forth. The source of that is Hooke's law. That's terrible Hooke's law, sorry. More specifically, it's the spring force Kx. And another type of oscillation we looked at was the pendulum, as I mentioned earlier. So the pendulum will obviously oscillate back and forth. What is the source of those oscillations? In this case, it was the force of gravity, or more specific, the component of the source of gravity in the direction of motion, which would be perpendicular to the string. So, but gravity, you could just say gravity is the source of the oscillations. If you turned off gravity, if you're able to snap your fingers and turn off gravity, there'd be no more pendulum. Whereas if you turned off gravity, there'd still be motion on a spring. So that's why we're talking about the sources of the oscillation. We talked about other sources of oscillation yesterday. We looked at vibrating strings. We could send a wave pulse down a string. That looks a little bit like this diagram down here. You send a wave pulse down the string, and the wave pulse kind of moves forward with time. What is the mechanism of the wave pulse in a string? And the answer to that is tension. When you send a wave pulse down the string, you have a force, let's say at a particle here, there's an upward motion, and when there's an upward motion, the adjacent particles pull on their neighboring particles within the rope or the string, and it pulls them up. I mean, picture you holding hands with a chain of humans, and one half of the chain moves forwards, and your hand gets yanked forwards with them. Right? There's a tension there in your arm that's pulling you forward. So that's the driving force of the wave in a string. It's the tension force. And you'll recall in lab 4, there's the equation that has, I think it's root tension over mu somewhere in the equation. And root tension, that's the force responsible for the wave. So the larger the force of tension, the faster the wave will move. And the other kind of wave that was very briefly mentioned yesterday, and we will not go into details about this at all, is water waves. So water waves are something like, waves that you see at a beach, or you drop a pebble in some water and you get a pattern that kind of looks like this. You see sort of ripples that propagate outward from the center of the source of the wave. These waves move forward, and what is the source of those waves? And the answer is actually twofold. It's actually partially gravity and surface tension. Now, we don't talk about surface tension in this class. That's more of a fluid statics concept. And there's actually a whole separate class on fluid physics. So we don't talk about that in first year physics very much. But anyway, I just want you to know that every single wave that exists, there exists a sort of source where if you turn off the source, the wave disappears. So back to sound, we know sound is a wave. So what is the source of the sound wave propagating forward? Even myself, as I'm lecturing right now, I'm generating a sound wave with my vocal cords, and the sound wave is propagating out of my mouth and somehow reaching the microphone. And then the microphone transmits it through your speakers, and then the speakers transmit the sound to your ears. How does that, other than the digitized sound through the webcam and through your computer, how does the sound propagate from my mouth to your ears? And the answer is actually quite basic. It's through a series of collisions. So what happens here is you have some sort of diaphragm either meaning like a speaker that oscillates back and forth, or your larynx that can oscillate back and forth, or your vocal cords oscillating back and forth. And when they oscillate back and forth, they physically jiggle the molecules that are touching the speaker. And when you jiggle the air molecules, we often forget this, but air is a fluid, and there's actually a lot of particles that were just invisible to our naked eye. But these air particles that I can't see, I can feel them. When I wave my hand around, they're definitely there. I can feel wind. When you jiggle one, they run into their neighbors. I mean, it's kind of like driving on the 401 during rush hour. If one person rear ends you, you bump forward and you hit the person in front of you, right? That's pretty much how air molecules will collide with one another to propagate or carry the wave forward. So you get a series of jiggles, and that is how the sound will reach your ear. And if we had more time, we would talk a little bit about how your ear actually interprets the sound. Pretty much, in a nutshell, you have a membrane in your ear, and when the air particles reach the membrane in your ear, they jiggle the membrane in your ear, and there's a mechanism in your ear that can sort of interpret that as electrical signals, sending them to the brain, and then your brain learns how to, over time, intuitively, your brain learns how to, decode those electrical signals and turn it into sound. Your brain is actually a very, very wonderful, complicated thing that most scientists, I don't even think science is even close to fully understanding how the brain works. I mean, we think we know a lot of features about the brain, but there's a lot about it we don't know. Anyway, point being, since back on point, I digress. Now that we know the air is responsible for carrying the sound forward, we can then say, well, it doesn't have to be air. It could be almost anything, right? The source is adjacent collisions. So air is nice because humans can live and breathe and thrive in air, but solid objects also have neighboring particles and molecules. So if you jiggle molecules in a solid object, that will also propagate forward. And you might remember from grade 9 science and especially first year chemistry, that solid objects are more dense than air. Go figure. Here's your PhD. You now know that solid objects are more dense than air. When you have a higher density, the molecules are closer together. And when the molecules are closer together, it actually makes the propagation much easier, more efficient, and much faster. So, for instance, let's not even take a solid, let's take a liquid, like water. If you're underwater and you try to speak, it sounds muffled. That's different. Sounding muffled is different then the speed at which the sound will propagate forward. We'll talk about a little bit about that later, but I do want to say, believe it or not, if you were to, let's say, go underwater in a pool and you had goggles on so you could open your eyes or whatever, and you take a bit of a rock and you kind of hit the bottom of the concrete pool with a rock, you can hear the collision between the rock and the bottom of the pool, and you can actually hear that perfectly across the pool. If you had a friend of yours in the deep end of the pool and you were hitting the rock in the shallow end of the pool, the person in the deep end of the pool could hear that rock, no problem. And that's because water is more dense than air, and it actually carries that sound much more efficiently and faster than you would in air. So the moral of the story here is, depending on the medium, you're going to have a different speed of sound, and that is caused by the fact that these molecules are closer together or farther apart in different media. So, you know, for instance, air, the speed of sound in air is about 343 meters per second. Now, don't get me wrong, 343 meters per second, that is incredibly fast. We actually call this Mach. So Mach 1, you might have heard the phrase Mach 1, Mach 2. When you say Mach, that is the speed of sound in air. Now, things that are more dense than air, you would expect, knowing the fundamental propagation mechanism of sound, you would expect the speed to be faster. So if you look at this, if you had something like glass is a solid, look how fast sound travels in glass. 4,500 meters a second. This is 4.5 kilometers per second. Think of how fast that is. That's incredible. Concrete, hardwood, you know, concrete is like, you know, what the bottom of a pool is perhaps made out of. Look how fast sound will travel through concrete. Even water, it's like sound travels like 3 times faster in water than it does air. I just find that fascinating, and it's such a simple explanation. As soon as you understand the mechanism by which sound will propagate, all of a sudden, these patterns emerge with ease, with very little thought. These patterns will emerge. Now, the exact numbers perhaps are complicated, and you could measure those empirically in a lab. But the pattern you should be able to very easily determine. You know, if on a test I say the sound travels faster in hot air versus colder air. Well, hot air has more jiggle. Cold air has less jiggle, you know, because that's kind of what makes air hot. I could ask you the difference between sound in concrete versus that of water. You should be able to know that concrete's a solid and water's a liquid. So, you know, all these basic concepts that, you know, I'm not exactly asking you to calculate exact numbers here, but the concept of the pattern should be fairly easy to determine. Okay, moving on. Characteristics of sound. Well, I can talk really loudly or I can talk really quietly. That is related to the intensity or the amplitude of the sound wave. And you can easily think about this, you know, if let's say the speaker oscillates with a large amplitude, then that's going to be a very loud collision on your own eardrum. But if the speaker oscillates very same frequency, but just with a lesser amplitude, then the force of the jiggle or the kinetic energy in the jiggle is lower. Now the jiggle will still have the same frequency, but it'll just be jiggling with a lesser amplitude. So on the receiving end with your ear, there's less intensity, there's less energy, so it'll come across as quieter. Pitch. I'm sure you know what pitch is. You don't need a physics class to tell you what pitch is. Pitch is related to frequency. That's the difference between an A or a G, you know, or two different notes. I mean, there's so many TV shows and movies that have the word pitch. There's Pitch Perfect, you know, Glee is talking about pitch, you know. Pitch should be colloquially known to be related to frequency. Pitch is one of those physics terms that sort of weaseled its way into everyday speech. So if I say, you know, your pitch is off or you're tone deaf, you know, I can't sing to save my life. So when I sing a song, everyone covers their ears because I don't have any pitch. I don't have any tone. I'm tone deaf. Anyway, moving on. Audible range. For the human anatomy, our ear is designed to only pick up frequencies. And we know what frequency is. We learned what frequency is with simple harmonic motion. It's 1 over the period. It's how many complete cycles occur per second. Our ear is only designed to pick up something as low as 20 hertz and something as high as 2,000 hertz. And 2,000 hertz is something that you can hear when you're younger. As you get older, that upper bound diminishes. And I remember when I was taking first year physics, how old was I? I don't know, probably around 18. I remember taking a hearing test online just for fun. And at 18, I could easily hear 2,000. In fact, I could probably hear I think I remember being able to hear above 2,000. And now, more than 10 years later, actually, even yesterday, I retook the test just because I was curious, because I knew we were going to be doing this today. And I can no longer hear 20,000 hertz. I can hear close to that, but I can't hear 20,000 hertz anymore. And that's perhaps due with just natural aging. The other thing that might affect this is like hearing damage. If you are in a job that is close to, a high intensity of noise, like let's say construction work or like power tools, or even a sound engineer where you've got earphones on all day and the sound is kind of right in your ears close up, that can actually speed up the deterioration of your ear, and you'll lose your upper limit faster than someone else would who takes better care of your hearing. Now, here we have to use some understanding of the English language. As I said before, physicists are not really good with words, so we try to label things and name things intuitively. If we use the phrase ultrasound, ultra meaning large, good, ultrasound means above sound. What does sound mean? Well, sound is things that we can hear. We as humans can hear. So ultrasound just means frequencies of sound above what a human can hear. A different animal, all bets are off. It is well known that dogs have quote unquote good hearing. So a dog's ear, anatomically speaking, is designed to hear frequencies much higher than 20,000 hertz. That's what dog whistles are. When you blow a dog whistle, we as humans don't hear anything because our ears are not designed to hear frequencies that high. But a dog, to them, it just sounds like you're talking. They just hear a whistle being blown. Same thing with cats. Cats are also designed to have really good hearing. In fact, many other animals other than humans have better hearing than humans. That's kind of funny. Again, I'm digressing. Back to this. Infrared. Infrared has, if you know the English, root meaning for infra. Infra means below. So infrasound. And you may have heard infrared radiation. Infrasound means below sound or below what a human can hear. So it's below 20 hertz. The phrase infrared means below red light. We'll talk about light in the next semester, 137. And ultraviolet means above violet, means above blue. So again, we'll talk about ultraviolet and ultra-red in 137. But these sort of root prefixes in the English language we borrow because they make logical sense when we're labeling things. Okay, we have this notion of intensity of sound, and you can measure intensity with a unit called decibels. And you may have heard this if you were to ever look into a sound system at, say, Best Buy or what have you. Decibel is counting powers of 10 of the intensity. The intensity can be quite large numbers, so we use a different scale because it's kind of weird, or sorry, not large numbers, small numbers. It's quite weird to say, oh yeah, I have my radio set at 10 to the minus 12 watts per meter squared, like 10 to the minus 12, what kind of unit is that? It's just a mouthful. So what we do is, because they're on such small orders of magnitude, meaning 10 to the minus 12, we talk about the negative log. In chemistry, what do they call the negative log? They call it P, right? pH, the negative log of the hydronium ions. So we use negative log as well. So the negative log of the intensity will actually give you the decibels. So here, to get rid of the negative sign, we actually compare it with the threshold of hearing. So if we want the intensity of let's say, your stereo system, we say, well, the intensity of your stereo system in decibels is going to equal 10 times, and I'll get to that 10 in a second, 10 times the log of the intensity in watts per meter squared of your stereo compared to the threshold of hearing. The threshold of hearing intensity, meaning if it was any quieter than this, the ear wouldn't be able to pick it up. The threshold of hearing is 1 times 10 to the minus 12 watts per meter squared. So it's a relative intensity. So you say my stereo system is 4 times as loud as what your ear, the minimum intensity that your ear can hear. Now, why do we multiply by 10? Simply just because the log of the division is it's still small. So that 10 is sort of a fudge factor. Now, please understand here, this is an invented scale. It's invented, just like Fahrenheit. Now, we don't really use Fahrenheit here. Your parents will. Your parents are probably of an age where Canada, they were growing up in Canada where Canada still used Fahrenheit. Fahrenheit is a completely invented scale. And once the scale is sort of established and people have a feel for, the intuition, like, oh, if I tell you my house is at 63 degrees Fahrenheit, do you know, is that warm or cold? Like, I don't know, I'm a Canadian. I don't really have a good intuition of Fahrenheit. Decibels is just an invented scale, just like Fahrenheit. So why is the 10 there? Because it's convenient. There's no mathematical reason why the 10 is there. It's just because it's convenient. If you did the log of I, the intensity, over I naught, the numbers are just too small. So we just multiply by 10 to make them nice numbers. And you can say, oh yeah, my volume is at 12 decibels, or my volume is at 3 decibels. That way we don't say like 0.3 decibels. So it's an invented scale. We can make whatever rules we want, and as soon as the scale is used commonly, we become familiar with kind of the we become familiar with what the numbers mean. Just like pH, a pH of 7 is neutral. Well, why is that true? Well, that's just because of how we've defined the pH scale. Now that it's well established, we all know pH 7 is neutral. So beyond that, it's just once you have familiarity, it's just it's common knowledge. You just kind of use it from there. Okay, as with many things in nature, and there's an interesting side note about this, as with many things in nature, the intensity of sound actually diminishes according to the inverse square law. So this means if you had a sort of speaker, well, that's a terrible speaker. If you have a sort of speaker that is emanating, I'll color in the speaker. If you have a speaker that's sort of emanating sound waves, of course, when you emanate sound waves, it emanates in three-dimensional space, not just in 2 dimensions. So you have this sort of sphere, of sound that is over time expanding and getting bigger and bigger and bigger. Picture like an explosion. Like, if an explosion happens, you see the sort of shock wave come out as a sphere. That's how you can picture sound coming out of a speaker. It comes out as a sort of a hemisphere in 3-dimensional space. As it spreads out and as it gets farther away from the source, the intensity actually diminishes according to the inverse square law. And this shouldn't be too surprising because the surface area of a sphere is 4 pi r squared, which means as the sphere gets bigger, the surface area of the sphere is increasing with respect to r squared. And that means if the same amount of energy is being distributed along the sphere as the sphere is getting bigger, then the energy or the intensity would be decreasing with respect to 1 over r squared. So that shouldn't come as too much of a surprise, but you see this notion of 1 over r squared popping up multiple times in physics. You see it with gravity, gmm over r squared. You see it with sound. Spoiler, you're going to see it with electromagnetism in 137 if you are taking 137, if I haven't scared you off, in next semester. So this sort of notion of 1 over r squared comes up quite frequently in physics, and Einstein thought, hey, this can't possibly be a coincidence. There must be something underlying here that we're missing. And Einstein died trying to do something called unify all the forces. And what he tried to do was he tried to find a fundamental explanation that causes and explains all of the fundamental forces of nature, because all of the fundamental forces of nature seem to follow the inverse square law. And to Einstein, that was too much of a coincidence. But he never did it. He died trying to, and it remains unsolved. Einstein died right at the cusp of quantum mechanics. And since his passing and quantum mechanics has sort of taken off, we now have a better understanding why Einstein was having such a hard time unifying gravity and let's say the electric force. Because quantum mechanics shows that on a very subatomic level, things are very chaotic and not well defined. So we now know why Einstein was having so much trouble with it. But anyway, I digress. Physics is just too interesting. I can't stay on topic. Okay, anyway, moving forward. Oh, what's going on with OneNote here? Okay, so we've learned about basic properties of sound, but how do we generate sound? Very simply, the answer is things that vibrate. Anything, really anything that vibrates will make a sound. It could be a steel bowl that you have in your kitchen and you flick it with your finger and you hear like a ding. That'll make a sound because the metal bowl is oscillating or vibrating. In your vocal cords, your larynx, the way your voice and you as a human produce sound is there are muscles in your vocal cords that you're not even aware of. And you can change your pitch by changing the tension in your vocal cords. And as we know from your lab, when you change the tension in a string, it changes the frequency at which it vibrates. And the frequency is related to pitch, and the pitch is related to the note that we hear. So yeah, quite simply, how do we generate sound? Things that vibrate. So the simplest of things that we can talk about that vibrate are things like a string. Strings vibrate. I guess most noteworthy, the string that produces sound that vibrates is on a guitar. I mean, of course, there are other strings that vibrate that make sound, but like in a piano. But I guess a guitar is more colloquially known to have strings that vibrate to produce sound. So how do you play the guitar? It's all physics. Here, you have a bridge at one end of the guitar, and you have a bridge at the other end of the guitar. And when you pluck the string with your finger, then this distance, let's call it L, is allowed to vibrate. And you know from standing waves, you know from the previous lecture and having done your lab, that given a certain length of string, there are certain frequencies that will result in a standing wave. Not every frequency, but there's a certain frequency that will result in a standing wave. And the standing wave means that there's nice motion and the string will move kind of up and down in a nice coherent way and produce nice, smooth oscillations in the air for your ear to hear. When you have the full distance between bridge to bridge, you get one type of note because the length is long. If you place your fingers, I think they're called struts. Don't yell at me if I'm wrong, but I don't play the guitar. If they're called, let's say they're called struts. If you place your finger on a strut, what you're doing is you're effectively shortening the length of the guitar string. And now you have L2 is less than L1, which means a different frequency will resonate. A higher frequency will resonate. So as you slide your finger in, you're shortening the length and you would be increasing the frequency. And you can see that in the equation of your lab. You can see that as L shrinks, you're gonna get, what is that equation? Don't sue me if I'm recalling this incorrectly, but it's something like 2n over L root ft over mu, something along those lines. That I think that's actually correct, but if I'm wrong, don't sue me. But I know L is on the denominator, so you can see in this equation, if L goes down, you're going to increase the frequency, and that's precisely why. So that's the physics behind the guitar. A piano will also use these strings as well, but a piano, you don't play like a guitar. You don't use your fingers to change the length of the strings. Instead, what a piano does is it lays out every possible length of string separately, and they assign each string to a separate key on the piano. So a guitar and a piano have very similar physics behind them, but a guitar is much more elegant because it only uses 5 or 6 strings. A bass guitar uses 4, but it uses a very manageable number of strings, and you can use your fingers to implement some basic physics to actually create combinations of other lengths of string, all in one nice, easy, small, carryable device. Whereas a piano, they just brute force it. They say, no, we're just gonna manually lay out every possible length of string and then assign it to a separate key and then make it so much harder to play. I've been playing the piano for many decades, so I play the piano reasonably well. And I hate it because it was such a pain in the butt to learn, and a guitar only has 6 strings and it seems much easier to learn. But now that I'm older, it's harder to pick up a new skill. So I've struggled learning how to play the guitar. I've tried, I can't do it. My brain is not wired for it. I was quite young when I started learning piano, and it just kind of sunk into my brain. So anyway, the physics of a piano and a guitar are very similar, both of which are very cool. The other way we can get sound is, instead of vibrating a string, you can vibrate a reed, like in a clarinet. And a flute doesn't even have a reed. A flute, you can get sound by creating oscillations in an air pipe or an air column. Now, I don't know what happened to this slide here. That should say standing waves, as this should say. I don't know, there was a glitch in the export, I don't know, but that should say standing waves. So another way we can get sound is, instead of plucking a string and getting standing waves in a string, you can vibrate the end of an air column and then get a standing wave in the air column. Now, that's a very similar idea to a standing wave in a string. I know air has sound that propagates through like collisions in the air. I can't draw that picture very well, but for the sake of argument, we can pretend or represent mathematically the vibrations in the air, the longitudinal wave, as a sinusoidal wave. That'll help allow us to visualize this wave much more easily and allow us to create some math behind it. It's really hard to visualize a longitudinal wave, so you can artificially represent it using a sine wave if you'd like. So if you have an air column, like let's say this is the length of there's a T there, length of a flute. So, you know, that whole air column there would be the flute. And what you do is, you can, you know, with blowing air over the opening of the flute, you can introduce some sort of oscillation or driving frequency at one end of the flute. And what you end up getting, or what you're able to end up getting, if you blow with the right amount of speed, you will get also a standing wave pattern in your flute, in a very similar graphical way than that you get with plucking a string, for instance. So the first one, we call this the fundamental frequency, is when there is no node in the standing wave in the column. So the only nodes are here and here. And what we do here, the way we develop the math, is if this is a wave, then we see that the flute itself, or the cavity itself, represents only half of the distance of the wavelength of the wave. So then we simply say the length of the flute is half of the wavelength. Now, if you blow faster air, and if you have any experience playing a wind instrument, you will realize very quickly, you were probably taught this very quickly when you took lessons, either in school or privately, that when you play a wind instrument, when you play a higher pitched note, you have to blow faster moving air. The reason for this is faster moving air will cause faster vibrations. Faster vibrations is a higher frequency, so a higher frequency will cause a different standing wave pattern. And a different standing wave pattern, you might get one node. So that's what we call, when you do get one node, that's what we call the second harmonic. Now, you could be asking yourself, but Mark, you could, the speed at which you blow air into a flute or a clarinet is a continuous function. What happens if you blow air at an in-between speed that isn't one of these proper speeds? You're right, that could easily happen. What ends up happening is the instrument sounds bad. You squeak. If you ever play the saxophone, you can hear squeaking all the time. That means you're not, your mouth is not producing the right velocity of air to support the note you're trying to play, meaning you don't get a standing wave, and the wave pattern inside that instrument at the moment is not a perfect standing wave, and it just sounds bad because things are interfering and they don't constructively interfere properly, and they don't produce a nice net result, and then they just sound bad. So yes, you're absolutely right. You could blow into an instrument without the proper velocity, without the proper frequency. It's just not going to sound good. So between, well, we've got 0 nodes, 1 node. The next possible nice pattern is when we have 2 nodes. And we kind of went over this yesterday. This is going to be 1 wavelength plus a second wavelength, or sorry, a half a wavelength. So here we see that the length is 1.5 lambda, or 3 lambda over 2. So the way in which we develop a formula here is we go by node number. We know a standing wave occurs when there's a node, a nice node pattern inside. And to get to the next pattern, you just increase the number of nodes by 1 and then redevelop your relationship between length and lambda. Now, we have other possibilities. You can have instruments that are open at one end. So for instance, please recall here we have closed at both ends. Another one, we have open at one end and closed at the other. If you have an instrument that's open at one end, like a saxophone or a clarinet or a flute. A flute's closed at one end and open at the other end. Same with a saxophone, closed at one end, open at the other end. Clarinet, closed at one end, open at the other end. If you have an instrument like this, then when you have a closed end, if the air particles try to jiggle against a closed end, then they can't jiggle because it's a solid, and the particles in the solid aren't allowed to physically jiggle up and down. Whereas the open end, if you have an air particle here that wants to jiggle up or down, it can, because there's nothing stopping it from moving up and down. It's open, it's free. It's open to the air. There's nothing preventing it from jiggling up and down, so it'll physically move up and down. In this case, we have a slightly different allowable pattern. So I guess fundamentally here is we want an allowable pattern. And when you have closed at both ends, allowable patterns are the ones that have nodes at the fixed ends because they can't jiggle, and then you have any nice number of nodes equally spaced kind of in the middle. So 0 nodes equally spaced, 1 node, 2 nodes equally spaced, 3 nodes equally spaced, etc. Here, this has to be a node, and then this has to be open, and then we develop our pattern from there. So the first one, for instance, we have a standing wave that looks like this. This string oscillates up and down, or the air particles oscillate up and down there in a nice, neat, coherent way. However, we see if we were to complete the pattern, this distance is only 1/4 of the full wavelength. We go from 0 to the maximum to 0, 0 down to the minimum up to the equilibrium again. So that distance is only 1/4 of the wavelength of the whole wave. Now the next allowable pattern is when, again, this has to be open and at a maximum. So the next allowable pattern is 1 node here. And then you can see, okay, well, if I were to draw a sine wave, then if this is my flute, if that's my L value, how much of a lambda is that L value? And you see here that this distance is 3/4 of a wavelength. In fact, we're only missing that. So here I would say L equals 3/4 of the wavelength, which is exactly what we see here. And same goes for adding nodes. So that's how you can develop your pattern. Now, how does this help us solve things? Well, we have lambda. We can relate the length of the pipe or the length of the instrument to the wavelength of the sound that's produced. But wavelength isn't everything. We hear pitch, we hear frequency. We don't hear wavelength, we hear frequency. So how do you relate wavelength to frequency? How does this help study sound? And the answer is the wave equation, V equals F lambda. So we say the frequency is going to be the speed of the wave over lambda. And we know how to relate lambda to the length of the pipe or the length of the instrument. So if you know how long the flute is, and you know you're playing your instrument in air, we know the speed of air is 343 meters per second, then you can relate as soon as you know the length of the instrument, you can reverse calculate what the frequency you're going to hear is. And in fact, this is exactly how, if anyone's taken band class in high school, this is exactly how your music teacher will tune the class. You know, he'll have the piano play an A, and then he'll say, okay, you on your saxophone, play an A. And he'll play, and you're like, oh, no, that sounds flat. If you sound flat, that's a problem. So then your music teacher will say, okay, push in your mouthpiece a little bit. And as a student, you're thinking, well, what the hell is that gonna do, push in my mouthpiece? What's this stupid teacher? But what you're doing is, when you're pushing in your mouthpiece by a few millimeters, you're shortening the instrument, meaning you're increasing the frequency. And then if you're a little bit flat and you shorten your mouthpiece, you shorten the instrument, you increase the frequency, all of a sudden, you're right perfect on pitch. So that's why music teachers, they need to have a really good ear. They need to hear and be able to tell whether you're sharp or flat, and then they can say, okay, you're flat, push in your mouthpiece a little bit. Or if you're on a flute, you can say, oh no, you're flat. You know, flutes come in 3 pieces, maybe two pieces, and they slide in together. So if you're a little bit flat, you know, your teacher might tell you to push your flute in a little bit more. Or if you're sharp, he might tell you to pull your flute out a little bit. Things like that. So there's a lot of physics in music. It's quite remarkable. Here's the open at both ends. We've already talked about open at both ends, so I guess this is a bit of a repeat. So here we're at a demonstration now, and this is where I said if you were listening in kind of the 10 minutes before the lecture started, I played 2 songs for you. I played Crazy Train and Final Countdown. And I've been wanting to build this as a demonstration for 4 years now, but this thing is massive. And apparently, I'm told, we don't have room to store it at UTM in the physics department, so I have not been able to build it. But what this guy has done is, as you can see in the picture here, he has taken plastic piping, PVC piping that you can get at any hardware store, and you know, he has bent it around into various shapes to make it compact. But overall, it's the length that matters. Now, it's a little bit more complicated than that. When you introduce a bend, you can change the acoustics of the pipe and stuff like that. We're not going to get into that. You can literally do your whole PhD in the physics of sound. I mean, like, it eventually becomes quite complicated. But anyway, point being, because he needs this to be compact, he has bent the tubes around to achieve the length he needs for the note that he wants without making the thing massively tall or massively wide. And what he's doing is he's whacking the top of these pipes with a mallet. And when he whacks the top of the mallet, that is, you know, kind of like hitting the drum or blowing the mouthpiece and initiating a sort of a jiggle vibration at the opening of the pipe. So depending on the length of these pipes, he can control ahead of time what note he wants to play. So he's pretty much made an air version of a piano. Instead of plucking strings, he is plucking the air. And the length of the air column will change the pitch that he gets. So here's the YouTube video. I've tried to embed the video in the OneNote page. So let's hope this works. I'm sharing my computer sounds. I'm gonna play the video. If you guys don't hear the sound, please jump on the chat pretty quickly and I'll see and I'll maybe open it up in YouTube. But anyway, please enjoy the video.
So yeah, this is my PVC instrument. I actually built this one exclusively for LMU, as you can tell by the colors. So enjoy. Okay, I'll be doing a medley of songs that you might recognize. Ready? Yeah, you're ready.
Okay, welcome back. I hope you enjoyed that as much as I did. I've been showing that video to my students for the past 4 years, and every single time I watch that, I get goosebumps. Not only is that just an incredible amount of talent and determination and practice for any given person to do, but I mean, knowing the physics behind that, it makes it just all that much, more enjoyable and amazing. So I don't know, I hope you were able to enjoy that. He kind of put a bunch of songs into there. I didn't recognize all of them. I suppose I could look them up. It's probably in the description of the YouTube video, but what I did recognize was Mario Brothers, the theme song. There's In the Hall of the Mountain King by Edvard Grieg, the da 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 da. There was Bad Romance, Lady Gaga, Viva La Vida with Coldplay, there was Heartless, Pirates of the Caribbean, and of course the two songs I showed you, Final Countdown, right at the end there with the duet, Final Countdown, and then there was Ozzy Osbourne's Crazy Train. And I've been waiting all semester to play you the Final Countdown song, because not only are we in the final countdown of the term, like we're like in the home stretch, it fits perfectly with the lesson because, he played that song in the video. So I've been waiting all semester to play you the Final Countdown in the 10 minutes before lecture started. So anyway, if you are not there for the 10 minutes before lecture starts, you have been sorely missing out. Okay, anyway, in summary, standing wave patterns can occur in two different ways. You can say either open at both ends or closed at both ends. It's the same, it turns out to be the same formula. And the standing wave patterns occur when you have, the fundamental frequency with n equals 1, the second harmonic with n equals 2. The second harmonic with n equals 2 is when there is one node present. When n equals 1, we call that the fundamental frequency. And that's with no nodes in the middle. And if you have open only at one end, like I mentioned, you just rederive the pattern using some basic, geometry is not the right word for it, but a pretty simple diagram. You can see the relationship here is a little bit different, and then the node numbers increase differently. They don't increase by ones, they increase by twos. So it's 1, 3, 5, 7, etc. Although these equations are fairly easy to derive, they will be given to you on the formula sheet of the exam. So if you are wondering what the formula sheet on the exam is going to look like, you can always, we're all from U of T, perhaps from different campuses, but we're all from U of T. There might be a few visiting students, but for the most part, we're all from U of T. You can look up past exams on the library website. You can just Google it, U of T past exams. And you can always look up my past exams from the previous summers. I'm using the same formula sheet as I have in previous summers. So if you want to know what's on the formula sheet, you can always look them up that way. Okay, one of the last things I want to talk about in terms of this before moving on to a different topic is what makes me sound different than you? What makes a piano sound different than a violin? And the textbook, I think, does a pretty shitty job at explaining this, in my personal opinion. So I'm not going to explain it the way the textbook does. Instead, I'm going to explain it this way, because I think it makes much more intuitive sense. Now, in person, when I teach this class in person, I literally bring in a piano, and I literally bring in a saxophone. Yes, I bring in a piano. Yes, I bring in a saxophone. I know how to play both of those instruments. And I bring in something called an oscilloscope. This is called an oscilloscope. An oscilloscope, oscillo meaning oscillation, scope meaning to see. So this item literally is a piece of the lab equipment that allows you to see sound. It allows you to see oscillations or scope oscillations. So what I do is I hold a microphone up to my saxophone, I hold the microphone up to my piano, and I let the students see for their own eyes what the wave shape of a piano versus a saxophone would look like. Unfortunately, we cannot do this, and I tried my hardest to find a YouTube video of someone doing this, but alas, no one has this on YouTube, and alas, the campus is closed, so I can't even go in to do it and record it for you. So I have to settle for this. It's not my first choice, but please bear with me. Let's say we want to play a note, let's say an A. For those of you who know anything about music, you'll know that middle A is around 440 hertz. So let's say this is going to be 343 divided by 440 hertz is going to equal lambda. That's going to be the wavelength. And what the equation I'm using here is V equals F lambda. So if I'm solving for lambda, it's just going to be the speed of the wave V over frequency F. So the physical distance here, peak to peak, is going to be 343, the speed of sound in air, divided by the frequency A, 440 hertz, and that'll give you the physical distance in meters. It'll be a very small number, but maybe you could say micrometers or whatever, but I guess distance units. So that's a true tone. If I play you an A using a perfect sine wave, it'll almost sound robotic. It'll be a very nice harmonic tone, very smooth, and it won't sound like any particular instrument. You'll hear it and you'll say, yeah, that sounds digital. Well, because it is digital. It's a perfect sine wave. What makes a violin or a saxophone sound different than a piano? What makes your voice sound different than my voice? It's the wave shape, the shape of the wave. We said before that an oscillation is something that's periodic. A pattern that will occur repeatedly. That pattern does not have to be perfectly sinusoidal. It just has to be repeating. So when you actually play a violin and you hold it up to an oscilloscope, like you hold it up to a microphone, the microphone goes to an oscilloscope, you see the wave shape looks like this. You see, well, let me perhaps draw it over a different color. You see, you get these sort of wiggles, right? But there's still a wave, there's still a period involved. Here, you see peak to big peak. That is your wavelength. Now, the wavelength is still in air, which means it'll have the same 440 hertz frequency. So when a violin plays an A and a piano plays an A, or your voice sings an A, let's say you're really good at training your voice and you can hit an A pretty easily, then you can tell, like, yeah, okay, I can tell that the violin sounds the same, it's playing the same note as you're singing, but I can tell that it's two different things. I can tell that there's one's a violin and one is a voice or a human. The reason you can tell that is because your ear and your brain is interpreting the different wave shapes. And to your brain, it says, okay, there's two different signals. One sounds different. Yes, it sounds like an A, but it sounds different. It sounds brassy, like if you play trumpet or any other brass instrument, you get the sort of metallic-y brass sound. It's often usually used in composition as like a regal sound, like, you know, a lot of kings and queens and, you know, monarchs will use regal sounding brass instruments. That's kind of historically how they've been used. So our brain associates that with a regal sound. And then percussion has a different sort of sound, and you can sort of hear that it's different. That's what you're picking up on. That's what your brain is picking up on. It's the wave shape. With a piano looks a little bit more recognizable, like a sine wave, but it's still a little bit different. You know, the piano, as you can see, will look like this. And it still has a wavelength, peak to peak, or, you know, crest to crest. You know, as long as you're taking one complete cycle, that's all that matters. And it's still going to be the same lambda as usual. So, you know, when you play an A on a piano, it'll sound like a violin playing an A in terms of pitch, but your brain will be able to tell it sounds different. Now, if you're happy with that explanation, great. Turn off your brain. You've learned something new. I'm proud of you for learning something new. However, if you're a little bit curious as to why this happens, here's how and here's why. Quite simple, actually. The answer is superposition. Here's what happens. The way you get these weird wave shapes is you can take one wave. Let's say you take the graph f of x equals 1.5 sine x. Well, what's the period of sine x? It's 2 pi, right? So the k value is 1, right? The k value is 2 pi over the period. So it's 2 pi over 2 pi, which equals 1. Okay, now here's a different sine graph, as you can see. But this sine graph is 3 equals sine 2x. Or sorry, f of x equals 3 sine 2x. So here, we have a different period. The period here is 2 pi over k. K is 3. Oops. K is 3. So my period is 2 pi over 3, meaning it has been compressed horizontally by a factor of 3, or sped up by a factor of 3. So if it's sped up by a factor of 3, it'll have a higher pitch. Now what happens is, if you play two of these notes together, then the superposition principle kicks in, and the waves will interfere with one another, and the net resulting wave will be whatever it's going to be. So when you superimpose two waves together, you get this weird sort of wiggle. And that is how an instrument will actually produce non-sinusoidal waves from sinusoidal waves. Superposition says you can get these weird wave shapes by adding sine waves of different frequencies. And that's what the textbook is saying here. The textbook is saying, and this graph is available in your textbook, this graph is saying the reason why the piano has a weird wave shape is because you have, when you pluck a string, just based on how the string vibrates, it's not perfect, based on how the string vibrates, you're going to get a little bit of frequencies in and around the sort of 2,000, 3,000 area. You're going to get a lot of frequencies in and around the lower range, like 440 hertz, like an A. So mostly it's going to sound like an A, but we have these sort of higher frequencies that are blended in with it. These higher frequencies cause little wiggles. The higher frequencies cause little wiggles over the overall sine pattern. That is how, they're called overtones. That is how different instruments cause different sound waves. And these overtones can be suppressed, these overtones can be amplified based on the acoustics of the instrument. There's a reason why the violin is shaped the way it is. It's to suppress certain overtones and amplify other overtones. There's a reason why the piano is played with the top open. Again, it's for resonate, it's to promote resonance and to suppress certain overtones and promote other overtones. And that is what makes instruments sound different than one another. On a related note, this is actually the same way we are able to make electronic instruments. When you buy an electric guitar or an electric keyboard and you can synthesize other instrument sounds, how does someone go about programming a guitar sound into a piano? Well, they record what the overtones of a guitar look like, and they can mathematically recreate that using individual sine waves of different frequencies, and then adding all the sine waves together. And then the net result will sound like a guitar. So there's actually a lot of physics in designing electric instruments, which is really cool. Okay, we're in good shape. I think it's only 12:21. I think we're in good shape to finish all the material by today. So hopefully we can spend the whole 2 hours on Monday doing exam review. We have two main topics to talk about. We have beats left, which we're about to talk about, and we have Doppler effect, which is really cool as well. So before I move into beats, because it is something a little bit different than the mathematical analysis we've been tackling, I'm going to take a momentary pause in delivering new content And I'm sort of going to open the chat here, and I'm going to address any fundamental questions or any questions you have about the material up until now before we move on. So if you've got a question, now's your time to type it. Now, I've done a lot of talking about tying things into real life. So if anything I've said sort of makes you question what you've seen in real life, or you yourself play an instrument, you've got a question, now would be a perfect time to ask that as well. When solving for period, what does K represent? Well, in math class, they use that notation. They use period equals 2 pi over K. In math, K is just the coefficient in front of that variable X. In physics, we say, like, if it's sound, we say, X equals A cos omega T. So T is my independent variable. The coefficient in front of T would be omega. Omega stands for the angular frequency. So I guess it's analogous to K in this case. Any other questions before we move on with beats? I've heard that digital song and records have differently shaped sound waves and hence sound different. Is that true? I would probably say so. When you sing live, I don't exactly know the root of where this piece of information comes from, but I'm going to give it a stab. I'll give it a try. So when you sing live in a concert, now modern technology is amazing, but presumably the premise of when you sing live in a concert, it's just your voice. So when you give a concert, you have to be talented, and it really showcases your talent. But when you record an album, and you're in a recording studio where there's no ambient noise and your voice is going through a computer, they can make little tweaks, sometimes it's a lot. They can make tweaks to your natural voice to make it sound on pitch. So, I don't mean to take a jab at modern celebrity singers, but unfortunately this is true. Not judging, it's just a fact. Because of the technology now with it's called auto-tune, you can go in and kind of modify someone's natural voice to sound on tune or on pitch. To get famous now, you almost don't need to have a talent singing. You almost need to be famous because of your character. People like Katy Perry or Miley Cyrus, they get famous because they're a presenter. Their character is what they're promoting. And yeah, they have natural singing talent, of course they do, and they're a performer, but the reason why they sell a lot of records is because they're auto-tuned when they sell records and on the radio. And that's why a lot of people sound like trash when you listen to them live, because their auto-tune can't keep up as quickly as when you have an album recorded. And that's why, in my opinion, music quote unquote back in the day was a lot better, because before auto-tune existed, in order to be famous, you actually had to have raw, sheer talent in your vocal capabilities. But anyway, I digress. I think that mostly answers your question. Why does a record label or a record or a CD sound different? It's because it's been processed. They've taken that voice and they've run it through some software, and they've taken the wave electronically, and they've altered the wave electronically to make the singers sound better. So perhaps that's where the root of your question is coming from. I hope that mostly answered it. Yeah, someone said facts. Yeah, no kidding. Okay, any other questions before we move on? No? Oh, it doesn't look like it. So good, that either means I'm with everybody or I completely lost you at the beginning of the lecture. I'm hoping that's not the case. I'm hoping you're more or less with me. So let's move on now. I've closed the chat, so Brandon can graciously answer any other questions that arise. So let's move on. There's all the theories in place. We've looked at the math. We've looked at the equations. We've looked at v equals f lambda. We understand that sound can be represented as either a sine wave or a cos wave. We've done all that. Now it's time to take a step back and look at some really cool properties of waves that have some really nifty implications. I absolutely love physics. You have no idea. Everything I look at, I see physics. And here's just yet another example. So I'll show you a website momentarily. Before I do, though, I want to show you kind of what a beat is. So if you have two waves, or two sound waves that have similar but different frequencies, and they're played side by side. Let's say you have the pink wave here. The pink wave is labeled at 50 hertz, and the blue wave is labeled at 60 hertz. Now, 60 hertz is a higher frequency, so it's got a higher pitch. It'll sound like a higher note. Now, mathematically, 60 hertz means 60 cycles per second. 50 hertz means 50 cycles per second. So 60 cycles per second means it's more compact. The wave is more compressed. 50 hertz is more elongated. So if you look at the wave here, they both start at the same time, but here, oh, I should be really writing this in blue for you. You see here, the blue wave completes one cycle before the red wave completes one cycle. So this is just building your intuition. Okay, moving on. Where am I going with this? Superposition. You add the waves. If you play two sound waves simultaneously, you mathematically add their amplitude, right? So the amplitude here is literally the height of the wave. The louder it is, the larger the amplitude. The quieter it is, the smaller the amplitude. So the amplitude is literally a distance. It's measured in meters or centimeters or millimeters, but it's literally a physical distance. So here, they're both the same value. So let's say this amplitude is 1. So if you add 1 plus 1, you get 2. Now, as you move forward, like let's say, let me get a different color here. Let's say at, let's say, where are we? Let's say here, we have a negative part of the wave, a negative red wave, and here we have a positive blue wave. So if we add those two together, we might get 0, momentarily speaking. And then as we move forward, your brain and physics, I guess, will superimpose these two waves together, and the resulting pattern you get looks like something like this. Now, what does that mean? Fine, we can get behind superposition. It's fairly easy to sort of figure out. What does that mean for us? Why is this important? Well, amplitude is related to the loudness of the wave, right? Now, that means when our ears reach this part of the wave, it's going to hear a lot of noise, so it's going to sound loud. When your ears listen to this part of the wave, you see the amplitude at this location is quiet. So when the wave hits your ear at this location, it's going to sound quiet. Now, if you look carefully, the only thing that's changing here is the amplitude. The period of this sum is actually constant. So here, peak to peak is this distance. 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 The lambda is not changing with time, which means overall, this is a constant pitch, but changing volume. So really what you're doing here, it's like you're listening to the radio and you're just constantly turning the volume knob up, down, up, down, up, down, up, down, up, down. And of course, that's just going to sound weird to listen to, but mathematically, that's what superposition predicts is going to happen. Now, this is a mathematical representation of what's going on. Let me show you a fun demonstration using simple harmonic motion with masses on springs to physically show you what a beat is. This is called a beat frequency. So let me show you using this website. Oh, I already have it over here, sorry. Let me change my screen for you to see. Okay, so what you see here is you see two springs. We know previously that a mass on a spring will cause oscillations, sound or oscillation, so this is a perfect analogy. What I'm going to do is, I can't draw on here, right, it's Chrome. So recall the frequency of oscillation of a mass on a spring. It's root K over M. Root K over M is the frequency, well, it's the angular frequency, but still, frequency. So you'll see here that the spring constants are the same. You see I've got a slider here. Oh, I started it oscillating, there we go. You see here that the spring constants are the same for each spring. So root K over M. The only thing that's different between these two springs is the M. Same K, different M. So they're gonna have different frequencies. Now, a beat frequency happens when you have two oscillations that are close together in frequency. And what we saw mathematically in the previous OneNote slide was that there are gonna be times when they are in sync, aha, no pun intended from the 90s boy band, when they're in sync and they constructively interfere and can cause a large amplitude. And then there's going to be times when they're out of sync, and out of sync means one is going to be up, the other is going to be down. So when you add them together, you're going to get zero. So let's actually set these into motion, and you're going to see that there's going to be a time when they're both moving together. That would be the beat frequency, and then there's going to be a time when they're moving opposites. And then as time goes on, they're gonna swap back and forth between being in phase and out of phase. So let's see what that looks like. So now they're opposites, now they're together, now they're opposites, now they're together, now they're opposites, now they're together. Now, I'm using light masses. It's a little bit fast, so maybe we can use a slightly heavier mass. There, heavier mass means it'll go slower. There. So they're slightly different. Actually, maybe these two are the same. These look the same. Let me stop them. Yeah, these two masses look the same. All right, never mind. Hold on. Let's stop these. So yeah, you can only see it with the 50 in the red. Yeah, so these two are slightly different masses. And you see sometimes they're in phase with each other, they're bouncing up and down at the same time, and then sometimes they're opposites, one down and one up. That is a physical representation of a beat frequency. Now, you're thinking to yourself, okay, I'm still confused. I'm with you. I'm trying to show you as many demonstrations as possible to get the point across. So, I have another demonstration for beat frequencies momentarily, but before we do, I want to kind of re-explain this a different way. Hopefully, the second explanation makes a little bit more sense. So come on, scroll to the side. There we go. So hopefully you can see my OneNote screen again. Now, if we take a tuning fork and we whack it, then let's say this tuning fork, let me maybe use red so it can jump out. This tuning fork is vibrating at 440 hertz. This tuning fork is vibrating at something slightly less. And we see it jiggles the air molecules. Now 440 is slightly faster. So you see here the lambda is smaller than this. This lambda is much bigger, right? That's because it's a different frequency. Now, if these two are being played at the same time and the sound is propagating through the same air as each other, then they physically add together. So here you have an antinode and an opposite antinode. So when they add together, they perfectly cancel out. And here you have a little bit of overlap. So here you have a little bit of overlap, so it's going to be a little bit loud. So that's what's physically happening here. Here is the sort of mathematical representation, right? Here's the 440 hertz Here is the 438 hertz. And when you add them together, you get a sort of envelope wave like this. So you get sort of a loud part, you get a loud part, and then you get a quiet part, you get a loud part, you get a quiet part. So it literally sounds like you're turning the volume up and turning the volume down, turning the volume up, turning the volume down. Now, the speed at which this happens is actually very simple to calculate. The speed at which this happens is just the difference, the subtraction between the two frequencies. So in the above example, it was 440 hertz minus 438 hertz, which is 2 hertz, which means you're going to hear it get loud and then quiet 2 times per second. That's what a beat frequency is. It goes loud, quiet, 2 times per second. That's what that formula means. So this here is called 1 beat. So this is going to be a second beat. So this is what a 2 hertz beat frequency would look like. 2 times per second, assuming this is 1 second and this is 0 seconds. Okay. What does that sound like? I'm going to open up a beat frequency generator, and hopefully if I do this correctly, I'm going to share my computer audio with you. So when I generate this beat frequency on my computer speakers, hopefully you can hear it on your computer speakers as well. So here we have one tone being generated at 500 hertz and a second tone being generated at 503 hertz. So the beat frequency here is 3, which means we should hear loud, quiet 3 times in 1 second. Let's see what that sounds like. Okay, hopefully you heard that, and you heard a little bit of a whomping noise. It kind of sounds disorienting. Now, 500 hertz is a little bit high. I cannot pull up my keyboard here. Hold on. Let me just reattach my keyboard so I can change the frequency here. Okay, so let's change this frequency. Instead of 500, let's say 50 and 53. Now it's not playing at all. Of course it's not. All right, hold on, let me try refreshing the page. Oh no, it's not working. Okay, hold on. I'm gonna try closing the page. I'm gonna stop sharing. Oh, that's lovely. The whole computer's frozen. Hopefully you guys can still hear me. Let's see what's going on here. Oh, there we go. I think I got control of the computer back. What fun. Okay, let's try this again. Aha, okay, it works. So let's see if I can change the frequency. Nope, not playing. Okay, hold on. Let's try 100. Oop, not 400. Let's try 100. And let's try 103. Okay. Now I see the chat going. Is that just a question or you can't see something? Oh, someone said it is playing. I didn't hear it on my end. There's 100 and 103. I don't hear it on my end. I don't know if you hear it on your end or not. Okay, they hear, I don't know why I don't hear it, but I'm glad you hear it. You hear the whomping noise? Loud, quiet, loud, quiet, loud, quiet. Someone's saying it's really quiet. Okay, I don't know why I don't hear it. Maybe, let's try, see here, 400. And let's try 403. I was trying to get a lower frequency, but, oh, there we go. Now I can hear it on my end as well. So each time I'm doing this, it's a difference of 3. Now let me change that to, let's say, 6. So now the difference between 400 and 406 is obviously 6. So you should hear a beat frequency of 6. It should get faster. You should hear more loud, quiet per second. You hear that? And if I reduce it to, let's say, 400 and 401, you hear a very gradual loud, quiet, loud, quiet, loud, quiet. So that's what a beat frequency is. Let me slide us back over to OneNote. What is the chat saying? Depends on the quality of the speaker. Oh yeah, for sure. I don't know what you're listening. You might be listening on your iPad or your phone or something like that. Now, I have another video for you here. For those of you who are into music and have tuned your own guitar, because every time you pick up a guitar after it's been sitting for any length of time, you've got to retune it. If you've taken band in high school, you will hear your band teacher or the conductor in an orchestra. They'll have a piano play an A, and they'll say, okay, I'm listening for the A, play the A piano, keep playing the A, hold the A, and then they'll have each instrument systematically play an A, and they'll say, okay, saxophone, you play an A, and then they'll listen to see if you're out of tune. And the way they do that is the band teacher or the conductor will listen for a beat frequency. If I'm trying to play an A, and the piano's always in tune, so if the piano's playing an A, and I play an A, and there's a beat frequency, it means I'm out of tune. And the band teacher can figure out what you should do, because if they say push in your mouthpiece to make it shorter, if you make it shorter, you're gonna increase your pitch, increase your frequency. If you increase the pitch and the beat frequency gets faster, it means you're going in the wrong direction. It means you're going farther away. And if you push in your mouth, or if you push in your mouthpiece and the beat frequency gets better, it becomes slower, it means you're getting closer and closer to the perfect pitch. So this is an example of that. Let's just watch. Or not? Oh, there it is. It's coming slowly.
All right, in this lesson, we're going to be talking about tuning by ear. And we're going to talk about training our ear to listen to what we call a sum or a difference frequency or a beat frequency. And this is a frequency that is produced when we superimpose or we smash two frequencies together. So here's A, and this octave here is 440 hertz. This A represents the second string down on the guitar, which is also A. So if I take this guy and lower it just a little bit, down to say 438, I should have a difference of 2. And we hear that little wiggle in there. That frequency is what we want to train our ear to. Tune this guy up. So that the sum and difference frequency is 0. Now if I continue to go higher on this A string on the guitar and lift it above 440, say 442 or so, I have another sum and difference frequency. So now I'm going to lower this guitar pitch down. Again, we want to listen to the intermediate frequency. We don't want to listen to this. We don't want to listen to this. We want to hear the frequency that's being produced when we smash these two together. practice tuning and practice listening to that wiggle, that intermediate.
Okay, so that's an example of in real life how people use beat frequencies, to tune instruments and to determine whether or not two things are in tune with one another. I do this quite frequently when I have to tune my saxophone. When I was in high school, I didn't know any better. Your teacher will tell you to either push in or pull out your mouthpiece. But after your saxophone sits all winter, the metal contracts and warms up and stuff like that. And every time you put on a mouthpiece, it's not always put on in the same exact location when you're setting up your saxophone. So when I go to play my saxophone, I go walk over to my piano, I hit the A note. It doesn't have to be the A note. I mean, I use the C. I play an E flat on the piano, and then that's a C for the saxophone, just because it's in a different octave or a different key. But anyway, I don't want to get into that. And then I listen for that beat frequency, and I can tell if I hear a beat frequency, I have to adjust the length of my instrument by adjusting the mouthpiece. So it's a very, very, very fun implication of superposition, and it's a very fun implication of sound, and it's so cool. So anyway, we have a little bit of time left. In the last 12 minutes, I want to talk about something called the Doppler effect. This is, again, nothing new. No, we will have a new equation, so I shouldn't say nothing new, but there's no new physics. It's just old physics that's being applied to a new situation. And you'll recall that we started the class with talking about frames of reference. That's the very first thing we talked about in this class. We talked about a vector v from AC is vector v AB plus vector v BC. And we said when we add two things with the same frame of reference that are in the middle, it's as if they cancel, and you get vector AC. That was our very first thing we talked about in this class, was frames of reference. And we've seen that theme pop up repeatedly. Not only has it helped us mathematically to make our analysis simpler, we actually see here in Doppler effect that the frame of reference will actually affect what we actually hear. So it's not just a mathematical trick, it's actually a physical phenomenon as well. So I like ending the class with Doppler effect because it's a nice full circle. We started the class with frames of reference, we're ending the class with frames of reference, and there's a bunch of stuff that happens in the middle. Okay, so what is Doppler effect? Well, it is the apparent change in pitch. Apparent. It's not a real change, it's an apparent change in pitch. So what actually does this mean? I'll scroll back to the previous ones in a second, but in order to explain this better, this diagram helps me explain what this means. So here, if you have a source, this could be a speaker, this could be me talking while walking forward, this could be a train whistle as the train is moving forward, it could be a car horn as the car is moving forward, some sort of noise-producing object that is also moving forward. Why is the motion forward important? Okay, let's see. What happens is, oop, I touched something there. What happens is, at this location, the source will emit a sound wave, right? And then it'll emit a sound wave at a certain frequency. So at some amount of time later, it will emit a second one. And each of these will be moving forward at the speed of sound in that medium, maybe the speed of sound in air. So maybe it moves forward at 343 meters per second. Now, as these move forward, the distance between these is constant, because if you emit one sound and it moves forward, and let's say a half a second later, you emit another sound wave and it moves forward, both at speed v, then the distance between these two sound waves will be the same at every point in space. However, what happens if the source itself is moving forward? Then what happens is, at time equals 0, you have a sound wave that is produced, okay? And then at time equals, let's say 1, then let's say this is x equals 0. So then at x equals 0, the source has also moved forward and will produce a second wave, but the first wave will have moved forward. Let me switch back to red. The first wave will have moved forward, but the source has also moved forward. So this distance in here, is actually less than the wavelength of the sound that is produced. Now, I don't know why you would do this, but that's like throwing a ball and then running after the ball as soon as you throw it. It's like playing catch with yourself. You throw the ball, and as soon as it leaves your hand, you run after the ball and you try to catch it. Well, as soon as it leaves your hand and you run toward the ball, the distance between you and the ball is smaller than what it would have been if you just threw the ball and stayed still. So what you're doing here is you are actually shortening the apparent lambda. And we know the frequency is f over lambda. So the frequency is not f over lambda, the frequency is v over lambda. And the speed of sound in air is always 343 meters per second. But what we're doing is we are reducing lambda. We're making lambda smaller. We're reducing the apparent wavelength. So what that does is it raises the apparent pitch of the sound. That's called the Doppler effect. So that's what we see here in this first slide, that if it's at rest, the sound that is emanated from, say, a car horn or the sirens of a fire engine, they're all equally spaced. They're all equally spaced with a distance lambda. But if the fire truck is moving forward, then the distance, it's like he's throwing the sound wave in front of him and then driving after the sound wave. So you're actually making, the person standing here is going to listen to a higher frequency, and then here you're throwing the sound waves behind you and then driving away from them. So this lambda is actually larger than the initial lambda, and this lambda is actually less than the initial lambda. So this guy is going to hear a lower frequency, and this person is going to hear a higher frequency. That is what the Doppler effect refers to. Now, the Big Bang Theory has incorporated this joke into one of their episodes. So here's a very quick clip of the Doppler effect and Sheldon Cooper making fun of it.
So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Okay. Oh, there's my video. Where's my video? Here's my video. Okay, all right, I'm back. Technical difficulties, sort of. So yeah, that's the Doppler effect. Sheldon explained it in very quickly and in very concise terms. It's the apparent change in pitch due to relative motion between the observer and the source. Now, we can complicate things a little bit. We can also get the same apparent change in pitch when the source is stationary, but the observer is moving, right? Because it's a frame of reference. So if the source is stationary, but a car is driving toward it, then you are running into the wave fronts much faster than you should be. So you'd be, in this case, if the observer is approaching the source, then it would sound higher pitch than it usually would. So we can combine both of these ideas, and I don't want to go through the derivation, but we can combine both of these ideas, and we can say that the Doppler effect produces this formula where we can see that the frequency of the listener, or the frequency that the listener hears, is going to be a function of the source frequency, and the function is going to be the speed of sound in air, or whatever medium they happen to be in, whether it be water or whatever, plus the velocity of the listener, right? The listener could be traveling toward. If the velocity is backwards, then it's obviously negative VL instead of positive VL. And then we divide it by V plus Vs, the velocity of the source. And again, if the source is traveling towards you, it's negative. And if the source is traveling away from you, it's positive. Okay, so this is the equation for the Doppler effect. And it governs and explains mathematically the exact amount that the pitch will change that the listener is going to hear. And okay, I hate to be anticlimactic, but that is the end of the new material. And I'm going to have to run. I actually have a meeting at 1 o'clock sharp with a bunch of important people. So I have to jump. Maybe Brandon can stay on for a few minutes and handle any last minute questions. On Monday, we will do this concept problem on Monday. We'll do maybe 1 or 2 questions that involve beat frequency and Doppler, and then we're going to spend the rest of Monday doing exam review. Okay, guys, it's I do have to run to my other Zoom meeting in 1 minute, so I have to pop out. Brandon, I'm hoping, can stay for a few minutes and answer any last minute questions for you. Okay, see you guys. Thanks for coming out. And you can always email me if you have any last minute questions. Ciao, see you on Monday. Good luck on Friday, and please be sure to practice crowd mark. Okay, ciao guys.